Good afternoon and welcome to this Quantum Pulse session. This is our monthly session, which is driving awareness on deeper topics in quantum across the ecosystem. When I say deeper topics, I mean that we're no longer discussing what is a qubit and general awareness of quantum, but going more specific. We've done that in the last few years, and now the focus is to discuss more interesting topics, go a little bit deeper, and as part of this quantum pulse sessions, we have been focusing on a wide variety of topics, from industry applications to policy-related discussions, geopolitics, and so on. And what we are also doing, and this is the first session of this kind, is that we are looking at some of the latest developments that are happening in specific quantum related areas and what are the possibilities associated with that. So today we will be talking about quantum speed limits, and we have with us a very distinguished panelist. We have Professor Adolfo del Campo, who's a full professor at University of Luxembourg. We have Professor Arun Pati, who's the Director Center for Quantum Technology at KIIT Bhubaneswar, India, and he's also a director and a founding director at the Quantum Ecosystems and Technology Council of India. And we have Mr. Brij Mohan, who is a postdoctoral researcher working on superconducting quantum devices and computing group at the University of Oulu. So I think with that context, I'm going to be requesting the panelists to give a brief introduction about yourself in terms of the work that you're doing. Please take less than a minute to do that introduction, and then we'll dive deep into the questions that I have. Over to you, Adolfo. Professor Adolfo, can you introduce yourself, please?
Sure. So first of all, thanks for the invitation to be here. It's really a pleasure. So as you say, my name is Adolfo del Campo. I work at the University of Luxembourg. I'm also affiliated to a center in Spain, the Donostia International Physics Center. More or less since I started doing research in my PhD, I have been interested in time in quantum mechanics and non-equilibrium processes, mainly in quantum systems, and studying what determines the time scales, what kind of universal behavior they have, and going essentially from the foundations to applications in quantum technologies. So that's a bit the context. Is kind of a long-term interest in non-equilibrium processes.
Thank you so much. Professor Pati, if you could introduce yourself now.
Yeah, so currently I am at Center for Quantum Technology at QETCI, Bhubaneswar, Odisha, and I have been working in this field of quantum computing, quantum science for more than 30-35 years. And my current interest is mostly on quantum speed limit, quantum acceleration limit, and application of these ideas to quantum computing, adiabatic quantum computing, quantum control, quantum battery, and quantum thermodynamics. So various things we are doing. Yeah.
Thank you. Brij Mohan, over to you.
Yeah, no, thank you. First off, thank you for inviting me to this interesting session. So I'm Brij Mohan, and I'm a postdoctoral researcher at University of Oulu. Here, my group works on particularly in broad and superconducting circuits, which is the one of the platform where you can realize this. You can quantum computing things. For example, you can run your quantum algorithm. Is kind of gives you one of the I think leading platform. So here I'm studying the kind of collective phenomena in the superconducting circuits, as well as I'm pursuing some of my other interest. One is like finding the fundamental limitation in the quantum physics. One is like, of course, in the dynamical perspective is quantum speed limits or thermodynamic uncertainty relations, and also exploring how these particular things affects, in the designing a better quantum devices.
All right, thank you. I think we'll jump into many of these topics as we move forward. So we heard everybody talk about quantum speed limit, and that is the topic of interest today. So Professor Adolfo, how would you define quantum speed limit, and what is the underlying physics or the geometry behind it? Could you take maybe 2-3 minutes to explain that?
Sure. So Yeah, I would say that, the basic question is to understand what's the time scale in which a process can take place. Physics is often interested with the happening of events. Something should happen, a chemical reaction should happen, an atom should decay, a quantum computation should be performed. Any kind of process you can think of, you may ask what's the time scale, the natural time scale. And you may also say, well, what's the fastest I can perform this operation? What's the minimum time in which that process can take place? And that's the basic question that quantum speed limits have tried to answer. Historically, this was first discussed at the level of time, energy, and certainty relations that we know since the times of Landau, so like textbook results in quantum mechanics. But what quantum speed limits have done is to refine and to provide a more rigorous, more satisfactory kind of minimum time for something to happen. Yeah, and a key, if I have to be a bit more technical, refining the concept, a key aspect is the idea of distinguishability of the states of the system. Yeah, so essentially they are based on what is called information geometry. So we think of a system being able to be in different configurations, different states, and a bit like we do with Newtonian physics, where we think of particles in Euclidean space. Now we introduce a state space for the system, and we will try to establish a notion of proximity, of distances between different states of the system. So a quantum speed limit is really a statement about what's the minimum time for sweeping a distance in a state space. What's the minimum time to do that? And in some sense, that quantifies the happening of the event. That's the mathematical description of the unfolding of the process. You go from an initial state to a final state, which is distinct. And you have been able to introduce a notion of distance, which tells you how far you have gone. And that's what quantum speed limits try to answer. Yeah.
Right. Thank you very much. And Professor Pati, if you could just expand on that and say, why is there a speed limit?
Yeah, I mean, because whenever you deal with the quantum system, it evolves in time. Okay, it satisfies Schrodinger equation, as you all know. And once it evolves in time, naturally, question comes to mind is, at what speed system evolves, So there is a change, something is happening to the system, and you would like to know how fast the state is going to change with time. So once you ask that question, then as Adolfo already explained, there is a natural metric you can define on a quantum state space. Basically, quantum state space is nothing but, in case of single qubit, is basically Bloch sphere, which is very familiar to many of, present generation, even students also. So it's basically dynamics happens for pure state, it happens on the surface of the Bloch sphere. So you can ask question, how fast it changes. So then you define a distance, then you define a speed, and that's how it enters into picture. So using all the notion, you can define this notion of speed limit. Yeah.
And how fundamental is this speed limit?
Yeah, to me, I mean, this is one of the fundamental consequences of uncertainty relation, you can say, like, Schrodinger-Robertson uncertainty relation. You can derive using this particular relation for two non-commuting observables. At the same time, you can also use the geometric idea that already Professor Del Campo mentioned, that given any two endpoints on the state space, you can define the metric, and the actual path system takes on the state space is always greater than equal to the shortest path you can connect two endpoints. So intuitively, you can imagine something like even in ordinary Euclidean space. Suppose a particle moves on a plane, you fix 2 points. Okay, depending on the force, the particle may follow some different trajectory, right? But there is always shortest path you can connect these two endpoints, and this actual path is greater than the shortest path, right? So this intuitive geometrical inequality will tell you also the quantum speed limit that we are familiar, since 1945. So to me, it appears to be a very fundamental one. Yeah.
Right. So, Brij Mohan, anything you want to add to this?
Yeah, just want to add the things like there are, as Professor Adelpo and Arun mentioned, that you have two independent ways, like you can derive this speed limit, one using the fully geometry of quantum evolution, or just using the Robertson uncertainty relation. And these relations are, I mean, if you just look at the unitary dynamics of the pure state, there could be more than one speed limits one can derive. They have named is like Margolis-Levitin bound, and the first one was the Mandelbrot bound, which depends on the energy distance divided by energy variance, and then the another people came up with, I think very recently in late 90s is like Margolis-Levitin bound, where I mean the energy variance is replaced by the mean energy, and there are some other proposals also. So these are the most which are, I mean, kind of people have found it useful.
And which are the most popular ones which are closer to getting validated
Uh, I mean,
physically?
there are many groups have like I think tested this particular in different setups, and I haven't gone through those works, but they have verified this Margolis-Levitin bound and Maelstrom bound. And since the other bound is like, if you'll go, it's bit I mean tricky to test them, as you have to measure the fidelity of some kind of temporal I mean fidelity between time evolved state and the initial state. This is one of the main challenge, but this is very fundamental, deeply rooted in every physical phenomena happens.
And what is the role? I mean, if I can ask this question to all of you, and you can decide who, if you want to talk about it, is that how does this, while we're talking about a quantum speed limit, how universal is this concept of speed limit? And could you expand that on that a little bit?
May I go for that? So,
Yeah.
yeah, just to provide a broader perspective. Yeah. So, I would say that, very early on, like 1945, there was this beautiful work by Leonid Mandelstam and Igor Tamm, the Nobel laureate, who introduced the first rigorous time energy uncertainty relation. In the same paper, they used the notion of fidelity to introduce a distance and to say, well, that way I can also derive this so-called today Mandelstam time energy uncertainty relation or speed limit, where the minimum time for something to happen is bounded, as Brigitte said, in terms of the inverse of the energy fluctuations. The higher the energy fluctuations, the faster you go. So that provides kind of the upper bound to the speed of evolution. Yeah. So you can only go that fast as the amount of energy fluctuations you have. Then there was the other bound, which replaced this by the mean energy. So then the mean energy became kind of a notion of the speed of evolution. By now, there's an infinite family of bounds that have been derived. So there are many. You can play this game because you can replace the notion of distance. And I would say that for any equation of motion, so these days we understand that this is not even restricted to classical systems, but can also be applied to, not only restricted to quantum systems, but it can also be applied to classical systems. So you have a time continuous evolution for any physical process. You can introduce a notion of distance in a state space and then try to bound the speed of evolution in terms of some norm of the generator of evolution. In the case of Schrodinger equation, that will be the energy of the energy fluctuations. In the case of dissipative open systems, maybe this is some Liouvillean. But you have a classical equation of motion, and maybe as well there will be a classical notion of something that steers the evolution, that generates evolution. So that will be the Liouvillean. So I would say it's very universal, and it actually transcends the framework of quantum theory from the point of view that it also holds for classical systems, and I would say for any system with a state space where you have different states and it's evolving under some equations of motion. So I would say it's very general.
All right, thank you. And Professor Pati, if you can tell us, why is this topic so exciting for quantum computing?
Yeah, I mean, this notion of speed limit, even though it was there since 1945, over last 10, 15 years or so, a lot of groups are taking interest, especially Adolfo and his group and many others, they're taking a lot of interest. And our group also, myself and my students, we have been doing a lot of things for last several years. And yeah, so coming to why this is so interesting now in quantum computing is this question naturally fits in the setting of quantum computing, because the question is so generic, so universally valid. You can ask in any context, because speed limit basically tells you the answer to the following question, that given two states, initial and final state, how fast you can drive your system from initial state to final state. And in quantum computing setting, exactly you do that, right? So what, to implement any quantum algorithm, what you do, you prepare your initial quantum computer in all, say, 0, 0, 0. Then you apply, say, Hadamard gate, create equal superposition of all, qubits, and then depending on the algorithm, you keep on applying your sequential unitary operator, okay? And then you will reach some final state, right? So once you reach the final state, you will read out the answer from final state. So basically the question is how fast you can drive your system from initial state to the state that contains your desired answer, okay? So because of this setting, this naturally fits there, you can use this field limit and answer this question. Yeah.
All right. And what about quantum sensing? Brijmohan, if you want to take that, I mean, does this impact
Yeah,
quantum
so
sensing?
as everyone says that the speed limit gives the lower bound and the time. Let's say you have an unknown parameter encoded in the system and you want to kind of find out the precision in that parameter. So that is can be estimated via error propagation formula. So you have some parameter theta and you have some estimator which is like by measuring a observable, let's say A, you can estimate that parameter. So the error propagation will give you the exactly what is the error in that estimation of that parameter. So that is the fluctuation of that observable and divided by the absolute value of rate of change of that observable with respect to that parameter. And but we know that using the speed limit, so this rate of change of observable is limited by speed limit. I mean, limited by it. If you just use this Robertson-Schrodinger uncertainty relation, is limited by delta A times delta H for just a pure state. When I mean since you are encoding the parameter by unitary transformation, so you just cancel it out. Then you will get that your error in that parameter is bounded by 1 by speed. And if you more generally want to say that speed in that parameter speed is the Fisher information. So these idea of speed limit and this parameter estimation, they are pretty much related in this particular context.
So help us understand a little bit more on. You spoke technically in detail, both of
Yes.
you, in terms of what it means from a technical perspective. But what does it mean to the future of computing and sensing? And so, is there a limit to how fast quantum state transitions can happen? And hence, does it limit computing in any way? Similarly, for sensors, is there a limit to the precision to which, today we have quantum sensors which can measure which are precise enough, at least in, who can measure the electromagnetic signal of a signal of a single cell, right? Now and then of course, does this get impacted in any way by some of this theory?
I think Professor Adelpho can go.
Yeah, Rodolfo, please.
No, I mean, maybe I can just, try to answer at a very elementary level. Yeah. So if the moment you acknowledge that for any physical process, whether quantum or classical, you have some notion of the speed limit, well, then it's just a matter of finding applications. Yeah. So it's in some sense not surprising that quantum speed limits have very diverse applications. Certainly, one is quantum computing, where the computational capability of a physical device is restricted by speed limits. This is how they became popular, thanks to the works by Seth Lloyd and others who emphasize this application. Also, my friend Norm Margolis emphasized, this is, the very naive understanding was that if your computer has this amount of energy, it will only be able to perform this many computations. Yes. So far, I mean, this is a bit too popular science kind of exposition, but the idea is that the amount of energy of fluctuations in a given process will determine the speed of the computation. But there are many other applications you can think of. So already in 2014 we realized that if you have something like a heat engine, or like the output power of that heat engine in the quantum domain will be also constrained by speed limits. So you can find kind of speed limits to or power bounds in these physical devices. How much power you can get out of this device. Then there have been applications to metrology, as Brigitte emphasized. So the whole theory of quantum metrology, which tries to estimate with precision a given parameter, a known parameter like a magnetic field or temperature or some other property of a physical system. You can do it using the same formalism. Essentially, you shift the emphasis from time to these other parameters you want to emphasize. And again, using the principles of information geometry, you can apply, find rigorous bounds on your precision and sensing skills with this device. But there's been many other applications. You can think of applying to chemical reaction rates or to chemistry. How fast can a chemical reaction take place? Once you acknowledge that they also hold for classical systems, well, in some sense, you have a whole arena of possible topics where you can apply it to. And my former postdoc, Luis Pedro Garcia Pintos, for instance, elucidated that you can even apply them to biological evolution in a very Darwinian sense. I mean, this is, of course, within the realm of mathematical biology, but there's similarly a notion of some equations of motion that one can describe for the speed of evolution in a Darwinian sense. And again, you can bound it, you can find bounds to the how fast a species can evolve according to this theory, which is established. It's called Hamilton's theory. And again, there will be something like a classical speed limit telling you if you want to go from one species to a different one, this will be the minimum time will be upper bounded in terms of the inverse of some kind of fluctuations, in this case, in the genetic pool. So it's kind of the same reasoning applied in a very different context, where you again introduce a notion of distance and a notion of the speed, and you find a minimum time for something to happen. But, the typical applications have been quantum computing, quantum metrology, quantum thermodynamics, and now physical process, in particular in thermodynamics and in chemistry.
So thank you. Professor Pati, do you want to add to the use cases in terms of any detailing you want to do?
Yeah, so in addition to what Adolfo mentioned, so we do have other applications of quantum speed limit in the context of quantum control, quantum battery, as I think I already mentioned that, and what else? Yeah, I mean, essentially these are things. I mean, already we discussed that. So bridge, if you combine everything, so you can apply in biological process, you can apply in chemical dynamics, you can apply in quantum sensing, you can apply quantum control, quantum thermodynamics, quantum battery. So
quantum batteries is more an application of quantum thermodynamics in that sense.
Yes.
Yeah, so there were works, I think, by John Gould, Kavan Modi, and others who first had pointed out that if you want to charge a quantum battery, or if you want to discharge it as well, there will be a minimum time for that to happen, and you can again use the speed limits to estimate it.
Yes, yeah. So like Bridge and myself, we have a couple of papers where we show how fast you can charge a quantum battery using speed limit. Also, we have a so-called reverse speed limit, which is not very many people know. In addition to quantum speed limit, which gives a lower bound to how fast you can evolve, we have proved something called reverse quantum speed limit, which tells you how slow you can evolve. That is, so t is less than equal to something. And that also becomes interesting in the context of like discharging of quantum battery. Once you suppose you charge your battery, okay, you like to you like to store the energy for longer duration, and battery would start discharging, maybe on its own or maybe due to interaction with the external world. So naturally, the question comes to mind is how slowly battery can start discharging. So there you can apply the quantum reverse speed limit, which we have discovered, and that has very important role to play also. Yes. Yeah.
So the idea is that it can't be slower than a certain value, right? You can only make it as efficient to a certain level in terms of the speed of discharge. Okay.
And let me add you, very interestingly, this reverse speed limit also comes purely due to geometrical consideration, on the quantum state space, like the speed limit is a natural consequence of the geometry of the state space. Similarly, this also is a fundamental consequence of the certain geometric quantities on the quantum state space. So it not just comes arbitrarily. Yeah.
So I'm going to ask a very theoretical and fantastical question: is that if the number of dimensions change in space, right, and if we are talking about then the speed limit would be different. So we live in a 4-dimensional world, 3-dimensional space, 1-dimensional time. But if we are talking about a higher dimensional state, then this would look different, right?
No. Just to interrupt you, I mean, when you say higher dimension, we mean the Hilbert space dimension of the quantum system. We don't mean this dimension of the ordinary space time.
But the geometry isn't tied to the number of.
No. This geometry is, we're talking about the geometry of the quantum state space, the abstract space. Yeah.
But it
It's
would.
still true. Yes, sorry.
Go ahead, Adolfo. Yeah.
Please go
No,
ahead.
I think this is still true. Your question is valid. Like as you
Very
change
relevant.
you will have some state space, and you can change the dimension. So you can look at a qubit, or you can look at a qubit, and the speed limits are, or you can look at a free particle with an infinite dimensional Hilbert space, and the way you establish these speed limits will be different. So yes, in some sense, it's very important to first identify what's the effective description of your system, what's the right state space, and then what are the configurations that you can even detect, because maybe there are some fundamental configurations that are you cannot even measure them. Yeah, so you need a good, accurate, effective description, which means in particular to identify what's the relevant the relevant dimension of your state space, and the speed limits will be dependent on that. They will also be dependent on the what's the dynamics of the system. Yeah? So if you think your system is isolated, fine, you know it. But very often systems are noisy, are dissipative, and then you don't really actually accurately know what's the dynamics. Yes, you can guess, you can approximate, you can describe it. If you have a very tailored system, as often in the case of quantum technologies, we like to have very artificial, very well-controlled systems. Maybe we'll have a good understanding of what's the actual dynamics, even in the presence of noise. But in a general process, it may be very difficult. So there's also a bit of an art in actually adopting this effective description. This brings me to a caveat regarding speed limits. They typically only tell you how far you go from an initial state. It tells you travel a given distance, but this distance may be relevant for your interest. If you want a process to unfold, maybe you wanted to go this way, like driving a car, and then you have driven a kilometer, but you went the wrong way. That's not going to help you, yes? So it's also important, and this is one of the limitations of the conventional formulation of the speed limits, that they are only telling you how far you go from your initial configuration. But they are not telling you where you go. Or there's this idea of fixing a target space, a target configuration, which is essential when you, for instance, in a chemical reaction, you want to say, I want to prepare this product. Yeah. Mm-hmm. So you know very well what you want to achieve. But if you just look at how far your reactants are decaying, then it's not useful. You just want to make sure that these reactants convert into the right products. Yes. So, for instance, one of the recent developments is try to incorporate this idea of initial configurations, but target final spaces. And we are working on what is called or what we call quantum transition rates. Which again resonates with basic ideas in quantum chemistry, in stochastic thermodynamics, where you actually want to drive a process, but you want to steer it in a given way. Yeah? In a given direction.
And I'm going to ask, maybe this is a stupid question, but does entanglement, how does entanglement impact these measurement of state transitions and the speed limit?
Yeah, this is very not a stupid question, very valid question. So very important question. Yes. So this was already answered by Seth Lloyd and Lawrence McConney and few other collaborators. Many years back, that if you have entanglement, in your system, then you can drive your system much faster. Okay. So, but again, this is not universal statement, but under certain Hamiltonian dynamics, they have shown that the answer is yes, it is possible to drive faster compared to what it would be otherwise without entanglement. Yeah.
Yeah, just so
this is something that. Oh, sorry. Go ahead, Bill. Please.
Yeah, so just like to add that, I mean, if you are going through entangled subspace, since you start from the state which is not entangled and going through the entangled subspace, there are certain kind of states. If your intermediate region we are forming like GHG state, you can really speed up your evolution. And this is the one of the reason, because of like people have shown that in the collective charging of quantum battery, the region will gives you the advantage. Professor Adolfo.
Okay, so if you
Oh,
have, so entanglement gives you an advantage for, and you've done this experimentally, I
Yeah,
understand, right?
no, this has been found, but not always. But for
Okay.
certain kind of entanglement, the one you like some kind of meteorological advantage, or I mean, scaling in the Fisher information, for that kind of entanglement, it is sure that you'll, I mean, it will increase your speed.
one natural application where this has been very much studied is sensing, is quantum metrology. Yeah, there are people understand even that if you have some quantum resources like entanglement, in principle, you can achieve better parameter estimation. Yeah, people also understood very early on. This was works by Susana Huelga and Martin Plenio and others, that even just a little bit of noise can destroy this meteorological advantage you get due to entanglement. So sure, entanglement can help you to speed the kind of evolution, to sense better a given parameter, estimate it better. But this advantage is not particularly robust to noise. Of course, you may then refine this statement and say that for given classes of noise, you can still do well even in the presence of noise. And for instance, this is the field of dissipative quantum metrology, and people like Shahar Alipur, Ali Reza Rezakani, and myself with Matthew Bow have been working on this kind of, what are the limits in sensing, in estimating a given parameter in the presence of noise.
Just to add, like, if you ask the question little different way, rather than asking like whether entanglement helps you, I mean, to speed up, you can ask like, since entanglement is a resource, like how fast you can prepare the entanglement, so you can extend this idea of speed limit for the preparation of the entanglement. Like, you want to prepare certain kind of entanglement or entangled state, then you can think of like what kind of Hamiltonian you can take or system you can take, so that you can prepare that in target entangled state in a minimal time. So you can pose the question in this way. Here also somehow like speed limits comes into the picture.
Okay, yeah. So let me shift gears on this topic. I think we've discussed quite a bit around just the theory and the applications at a high level. But so, what is the latest development that is happening with respect to what you are doing individually? For example, Brijmohan, what are you doing? The work that you're doing, what is the latest work related to quantum speed limits that you're working on?
Yeah, so as everyone mentioned, I think about quantum batteries. So before I'll just mention about the thermodynamics. So thermodynamics, as Professor Delphocan said, that you can bound the power, or let's say if you have a engine, you are bound. I mean, you try to bound the power, the amount of work I mean, your engine giving per unit time. If you are a refrigerator, then you can bound the cooling rate. Yeah, so then people can gone little step ahead, and they'll use this the one we were talking about, quantum metrology, this Kramer-Rao bound, which gives the precision on the unknown parameter. Using that, you can find out some kind of speed accuracy kind of uncertainty relation. It's like once you, I mean, kind of, let's say your engine is producing some kind of work, but it gives you have a high fluctuation in the power. Sometimes it give you more power, sometimes it's less power. So this quantity is quantified by the noise to the signal ratio. I mean, power fluctuation divided by power. And using this Kramer-Rao bound or speed limit, you can get this thermodynamic uncertainty relation that can give you the trade-off between power and the power relate. I mean, this noise to the signal ratio of the power, and it can give you like some kind of when you are have a more power, then you have a less reliability in the power. This kind of a relation, but not always universally true. But it gives you some kind of a relation. But the similar one can ask like the question, like, since lot more groups are trying, like when in the charging of the quantum battery, so they try to exploit the quantum entanglement more, especially I will say this collective evolution, so that they can get in a more power. But if you are getting the more power, but there could be a thing that you have there is a fluctuation in the power in the work. So we were trying to establish between some kind of a relation between the charging speed and the power fluctuation or the work fluctuation. And there are some recent work where we, since the speed limit being studied, that some sort of inequality we have showed that there is a certain part of for the just consider the case of unitary evolution, certain part of Hamiltonian which actually commutes with the initial state, and that part you can remove, at that significantly improve your speed limit bounds, as well as same idea you can use in the metrology. You can get a much tighter quantum Cramer bound.
So the way I understand it as an engineer is that if there is a possibility of leveraging this concept of speed limit, also in understanding that if I am devising a system which has multiple parameters, and if I can understand the speed limits associated with each of the parameters, that in order to make this system move in a certain direction of efficiency, I can understand that there's only so much I can do with X parameter, and I should shift my attention to Y, Z, and other alpha parameters when I look at how the system needs to evolve, right? So for example, in the battery case, if you have a certain material which you're using and there is a certain amount of limitation, there is a signal noise to power ratio, which is, noise ratio is high for a particular material, then you know that there's a limit to which you can adjust these parameters and get with the same material, but you may have to change materials in certain cases, right? So this is a very slightly stupid example because material change is the most obvious thing. But if there are multiple parameters, I think speed limit could play a role in this kind of decision making. Is that correct?
Yeah, so quantum batteries are little different. Here you have the, let's say, array of a qubit, which you want to excite or de-excite them, than the conventional batteries we are using. But
But you do
they
have
the
qubits from
yeah.
different materials, right? Different
Yes,
modalities.
yes. So you can charge or discharge, but here we only consider the time as a parameter. If you are taking the consideration of other parameters as well, so the problem will become more complex, something like a Brechistochrone problem. So that will become a bit harder. I think in this area, maybe Professor Adelfo Campo sheds some more light on this particular thing.
It's okay. So maybe I can just add, like something very fundamental and basic. Speed limits tell you it's really like a speed limit on the road. It tells you shouldn't cross this 70 miles per hour. I mean, of course, they are fundamental. So actually, at variance with those in the road, you cannot pass them. Yeah, you cannot go farther. But they don't tell you that your system is evolving at that maximum speed. So that's very, a typical process is much slower than the speed limit. If you really want to push the fundamental limitations of your computer, of your quantum computer, of your sensing device, then you typically have to act. You have to engineer it. You have to, like you are saying, you need maybe to explore other parameters, or steer the do something to steer the dynamics at the actual maximum speed limit. So this is closer to the notions of optimal control, or what Brigitte mentioned, the quantum brachistochrone problem, which is a formalization of the idea that if you want to go from one state to a different one in the minimum time, well, there's only a given process. There's a particular class of evolutions that satisfy this feature. A typical evolution goes much slower and is not optimal in any way. So you want to always drive at the maximum speed limit. Well, you typically need to act very strongly on the system. So this brings also to the ideas of one of the important applications of speed limits is in the context of quantum control. And there it has been very important because now we understand perfectly that if you want to drive a system very fast in an optimal way, you also need to act more strongly on it. Typically, when you control a system, you perturb it by adding some auxiliary external fields or by doing something on the system. And the magnitude of this perturbation, of these control fields that you add, is determined by the speed limits. Yes, so there's an equality. In this case, it's an equality you can really establish. The moment you are optimal, you are following this fundamental maximum speed, and you are driving the process in the minimum time. But then to do that, you need to act in a very particular way. One of the particular branches of quantum control where this has happened is in the context of shortcuts to adiabaticity. So it's like the idea of you try to saturate these speed limits using some counter-diabatic controls, some controls that steer the dynamics in the precise way, in such a way that you always make optimal use of your energy resources or your to maximize the speed of evolution.
Okay, thank you. Professor Pati, if you can talk about some of the latest work that you are doing in this space. I saw a paper from you recently, uh, which sort of prompted me to, internally in QETCI to discuss and see if we can have a discussion on quantum speed limit.
Yeah, so currently we are doing many things on quantum speed limit with my students, and especially Breeze and others also, they are involved. So in one of our recent work, we tried to derive something called exact quantum speed limit, which basically tells you not a bound, but a way to estimate accurately how much time system takes in going from initial state to final state. So that is called exact speed limit, and then we proved that the Mendelssohn term bound empty bound is a special case of our bound. That also follows naturally. And recently, Bridge and few of my students also, we have generalized this to open system dynamics, where system doesn't not a closed system. So they're also they use this kind of speed limit to explain some counterintuitive effect. Maybe Bridge can tell little later about that. And in one of my another recent work, I tried to prove something called quantum acceleration limit. This is a very new work. In the same spirit like speed limit. So speed limit basically tells you how fast you can change from initial state to final state, okay? But acceleration limit tells you how fast you can change speed of a system, quantum system, from some initial speed to final speed. And that is that goes inversely like fluctuation in the rate of change of Hamiltonian, okay? So in speed limit, this right hand side basically depends on the shortest path connecting initial final point, and it goes inversely at the fluctuation in the Hamiltonian, whereas the acceleration limit depends on the difference between initial speed and final speed. Sorry, opposite, final speed and initial speed, and it goes inversely at the fluctuation of the derivative of the Hamiltonian. So how, at what rate your Hamiltonian is going to change, that will decide at what speed you can change, sorry, at what rate you can change your speed, okay? So this kind of bound on quantum acceleration will have application in driven quantum systems where Hamiltonian depends on time, okay? If your Hamiltonian time independent, then obviously, in that case, your derivative of Hamiltonian is 0, so you won't have any, bound is will be not applicable. But in case of time dependent Hamiltonian, this will put non-trivial bound, like in additivity quantum computing, or maybe in quantum control, or shortcut additivity, what Adolfo mentioned. So in those contexts, this will have very useful applications. So this is very, very new, and I hope a lot of applications will come up. Yeah.
So if I look, I mean, given that this seems to have a lot of implications for quantum computing, how much is this community which is researching in this space collaborating with people who are developing quantum computers?
Maybe Adolfo can answer this.
Very tricky, I mean, for sure, speed limits are being used to estimate computational capability of physical devices. Yes, I mean, I think in some cases it's known that some elementary quantum logic operations are optimized to act at the speed limit. I have seen less about the complete algorithms where they are actually, unless very specific simple cases, kind of more textbook cases. In some of them, it's understood that they do saturate the speed limit. But when it comes to actually collaborate with experimentalists, I think many still have the feeling that perhaps speed limits can be conservative. Yeah, it's as I said before, like to saturate them, you typically need to act with some kind of control. So it's mainly the community of optimal control, both in theory and in the laboratory, that are really working in this direction. So that also brings to the as Rigil mentioned, typically to actually determine where your system satisfies or fulfills or saturates a speed limit, it's difficult because this requires measuring kind of observable, which is very non-local, related to this fidelity between different configurations of different, the state of a system at a given time and at a later time. There's a group that has been able to do this in a very transparent way. This is Andrea Alberti and collaborators. But for relatively simple systems still, like a single particle harmonic oscillator with ultra-cold atoms, they were able to do this. But for more complex systems, such as the ones we like to use for quantum optimization, which are better described like complex many body spin systems, I think there's still experimental research is lagging behind the theory. You can still use the theory to identify the time scale in which the process can, the minimum time in which the process can unfold. But I don't think there's important experimental progress there. Yeah. Again, it depends on the application. For quantum computing, I would say this is the case. But if you move now to quantum metrology, I would say people are, in theory and in the lab, always trying to achieve the optimal estimation to reduce the error. So you are always trying to saturate these bounds, which fundamentally they are kind of the same as speed limits.
Okay, all right. So I'll take a pause here and ask for audience questions, and then if there after that, if we have time, I'll come back to our own questions again. Any questions from the audience? People, if you want to understand better or you have questions on what has been said, please raise your hand. You can either write down on the chat or you can ask the question directly. There's some people who are joining now also. Okay. Any questions? Yes, Rohini, please go ahead.
Yeah, so first of all, very, very fascinating discussion. A lot of interesting thoughts, comments. I guess my question is maybe more general, that some of the discussions you had earlier in the conversation on different paths to the state space that a system can take, and therefore the interaction, and you talked about entanglement, you talked about fundamental speed limits. Especially in the context of computing, are there ways to nudge the path the system takes in a state space? Are there some fundamental thinking that's happening there? And you talk about entanglement, talk about material, but how are people thinking about that in the context of also error correction? That's one of the sort of, I was wondering what the connection is between the two.
So you take this question, Adolfo, or?
It's a diverse one, yes. So I don't know which angle to take. So yeah. I mean, so this I guess the speed limits are being used in very diverse ways. I don't remember now. Any physical operation, including the error correction, is going to be restricted by these speed limits. I know so there was like error correction, there was materials and entanglement. Entanglement, I think we already acknowledged that it's a resource, that it can speed the evolution, but it can be feeble, or it can be perhaps not robust to certain kinds of noise. Then if you are able to counteract this noise with error correction, then you may be able to restore this maximum speed. Now, the connection with materials maybe is harder because there are very different angles. I don't think that from a point of view of material science, people are concerned with the speed limits at the moment. But what we know for sure is that if you are driving a system from one phase to a different phase, like a bunch of spins from a paramagnet to a ferromagnet, you may be crossing a phase transition, and then you can again formalize these ideas of information geometry, try to identify proximity between these phases, and study speed limits. And as we know already from classical thermodynamics, things like the heat capacity diverges at a phase transition. And so this also reflects on the quantum Fisher information or in the quantum speed limits, in the quantum speed actually. So there's also a divergence, and this is very important for applications in computing, because this simple example of going from a paramagnet to a ferromagnet is kind of a completely idealized process of a computation where you try to prepare the ground state, which is the ferromagnet. The ferromagnet, yes. There is, in some sense, these ideas of crossing phase transitions and what are the speed limits for them are being used to inspire a family of quantum algorithms. So for instance, we know that using quantum control, we can saturate the speed limit. So we have done this for simple phase transitions, but then an elaboration of these ideas have given rise to a set of quantum optimization algorithms, which are called by now perhaps digitized counter-diabatic quantum algorithms, where you use some approximate controls to solve some optimization problem, which physically means we are trying to find the minimum energy configuration of a given complex system. And there again, speed limits and the possibility of saturate them is being used. I don't know to what extent that answers the question.
So maybe I can add from my own experience where speed limit can be of use, in quantum computing. So I'll give a very simple example, which I have found many years back. So if you think of this so-called Grover's algorithm, this finding this particular item in database. So we know it is optimal and it takes square root of n steps, right? So in that context, you can use quantum speed limit and you can obtain exactly this square root of n step from speed limit. And not only that, you can also imagine your evolution of the quantum computer from initial state to target state as a sequence of evolution along the shortest path. So what happens is what you can do is you can find the distance between initial state of the quantum computer in case of Grover search and the target state. Okay, then you find the distance between the initial state and the state at next iteration. Okay, so since we know that it evolves along shortest path along geodesic, so if you divide the total distance by this distance in one iteration, I have shown that ratio exactly scales to square root of n. And so you can get the speed limit. Sorry, you can get the query complexity in case of quantum computing in this particular case from quantum speed limit.
So then it should be possible for new algorithms also to estimate
Yeah.
using
So
this technique. Yeah.
Right. So one of the major goal in quantum computing is to design your sequence of unitary operator so that you can drive your system along the shortest path. Okay. So, yeah.
Right. And since Rohini asked about error correction, I remember Brijmohan, you did talk about error correction or error propagation, right?
That is different, that error propagation in the metrology I was
That was
talking about.
metrology. Okay, sorry,
Yes.
I sort of remembered it incorrectly. Yeah. But
Yeah.
then at some level, error correction is also about controlling and optimizing the states so that error does not propagate to a point where your qubits are useless, right? I mean, in that sense, so in that sense, the rate at which the state change happens for the errors that are introduced in the qubits could also use speed limit terminology to understand how effectively or in how many steps and what is the fastest route to actually correcting those qubits, isn't it?
Yeah, this area I think have not been explored much, but I mean in the error correction, you see that where the error coming, you kind of design some kind of a strategy to correct them error. So since that is a itself some quantum process, so you can correct the error. It will give you some. What is the time you'll take to correct those error? How efficiently you can do it, but not a very well tie up between these two things, in my opinion.
Okay.
Yeah, what I can imagine is the following, that when you want to do error correction, and want to implement that using the sequence of gate operation, there you can apply the speed limit in designing those gate operation. How fast you can design your gate so that you can implement those error correcting operations. So there you will have some application, but
So the speed of the gate operations themselves. That's what you
I've not seen any direct application of speed limit in error correction. Yeah.
right. But you're saying that the speed of the gate operations themselves. Yeah.
Right.
Okay.
There you can certainly apply. Yes.
Right. So there is a question from Laltendu Biswal. Is this speed limit dependent on quantum system chosen? For example, taking a superconducting qubit or NV center diamond, etc. Will there be a change?
I would say that the effective description is the same. If you agree, for instance, that it's kind of a two-level atom, or two-level is a qubit, and so on. As long as the effective mathematical description is the same, your model is the same. It's independent on the actual platform. Now, different platforms are going to have most likely different effective description. So the kind of noise, the kind of two-level system, for instance, you will have a split in between your energy levels, which is likely to be platform dependent. So the bound will be the same, but even already your gap, which determines the energy fluctuations, how fast you go, is likely to depend on the platform. So in practice, yes, fundamentally the same principles apply if the effective description is the same. Of course, if you have different sources of noise, or if you're Hamiltonian, your description of the system is completely different, then everything is different, and there's no connection.
I would assume that there would be differences based on the platform, and to connect this to what Professor Arun Pati was saying, in that case, it should be possible to see how gate transitions are impacted in terms of minimum and maximum speed, theoretically, depending on which kind of qubit you are using, Professor Pati, if there was some work to be done in that space.
Yeah, certainly. I mean, depending on this is a different question. So depending on the physical system, you would like to implement your algorithm, and of course, system will have different coherence time, different interaction, and so on. So that will control your speed of quantum system, and as a result, that will also control the time, how much time system takes. Yes.
Okay. So there's a question from Dhruv Sharma. Good evening, everyone. And my question is the context of charging and discharging of the quantum batteries. How are the speed limits connected to the charge density and charge transfer? Brijmohan or
You can take this maybe.
Yeah, so I didn't get the question properly. Maybe his charge transfer, maybe he wants to know like how much energy we are tries to inject in the battery. So you can get the bound on the power itself, the rate at which you are charging the battery. I mean the useful work you are injecting in the battery in that sense, or you can get the bound on the time itself, the minimal time you require to charge the battery, or there is another version you can get something like reverse speed limit, which can determines like what is once you charge the battery, maybe some environment or self discharging, something like that, what is the lifetime of the battery, one can determine it.
no, I guess the question is that if you're transferring charge, the battery is being used, then is there a correlation between speed limit and the charge transfer? And
Uh,
how and efficiency or the rate or whatever, right?
Yeah,
And
I would say that the speed limit is putting an upper bound to the charge transfer. You cannot do
right.
it faster than a given amount, and the speed limits are identifying that maximum rate for
Right.
charging or discharging.
Sure. Dhruv, does that answer your question? Do you have a follow-up question on that? You can unmute yourself and speak if you want. That answers your question. Okay, great. Any other questions? I I usually
Hi,
prefer audience questions towards the end because they actually force you to think in a different direction.
hi all. This is Lakshmita here.
Yeah, go ahead, please.
Um, my question is towards how this is quantum speed limit is going to help in quantum machine learning. So right now, a lot of things is happening in AI based. So, like whenever we are processing data in deep learning, or think about like the images, videos, it is taking longer time. How is it? Is this like QSL is going to help there? Or if yes, how we can leverage this one, and how effectively we can get to know how much before processing any videos or audios or images, we'll come to know this much time it will take. Mostly like training the models. If you think about AI models or uh, large language models, it's taking longer time to train. But can I come to know, or whether the QSL will give some hint to for the time it will take for the training or testing or getting the result out?
It's like uncharted territory, but okay, let's see if the panelists have an answer to that.
Yeah, because why I'm asking this question, we are working in this particular area. We are completely blind, or this is a black box kind of things, like how much time it will take to train a model, right? But every what we are talking here, like mostly in hardware perspective or in different research areas, a part of AI. Just I want to understand how it is going to help us.
So, just for context, in case it helps the panelists, I think when we talk about deep learning, one of the challenges that we have is we really do not have insights into the internal states of the internal intermediate states that are used by the model for the training. So it's like we use it. That's why he's calling it a black box, which means that we know that deep learning works because we have developed a multi-layered neural system, neural network, but we really do not have insights into the various state changes that happen in that system. So I'm kind of suspecting that speed limits may not be possible, but I'll leave it to you guys to speak on that.
I would say speed limits are always there, whether you can identify them
Yeah,
or
but
not.
in terms of whether we can use it,
That's
yeah,
going to be
yeah.
tricky. But like obviously, you are updating your neural network, you are fixing the parameters. So yeah, I mean, this also depends a bit on how you describe it, because in some sense you may say that you are adapting your Hamiltonian, yes, your generator. So you have some update rules. So typically you need to know, you want to formulate a speed limit, you need to know what are the equations of motion, so what are the rules of the game, and how your state changes. Without this information is hard. You may be able to provide some bounds, as to without being specific about the states involved, if you are able to at least determine how different they are from your initial configuration. If you have a notion of distance, a notion of distinguishability. So I mean, I don't have a precise answer. I don't think it has been worked out, or I'm not aware of results in the literature about this. I think it's a beautiful, interesting question. Yeah, I expect the speed limits to affect it, and maybe if I am allowed to abstract the question, I guess there's another aspect to it. Everyone is worried about energy consumption in AI, and perhaps the speed limits help to it may be, you see, according to quantum speed limits, oftentimes the energetic cost of a given computation is much lower than that in the classical setting. Yes. So you may so there's a hope for having a quantum advantage in the energy cost for computation that may be relevant to machine learning in the future. This is, again, I think there's some work in this direction, but not much has been done. But again, it will be very interesting, yeah, from the point of view that these days people are even considering to power some AI centers even with a nuclear reactor, given the huge amount of energy consumption. So maybe we should think also about whether there are more efficient ways to train, which have a low energy cost, and whether quantum can help in quantum machine learning. That was part in the question. So what will be the energy cost and the time scales involved? Yeah, but I suspect these are essentially at the moment open questions. So very interesting. So thanks for the question.
All right, thank you. I hope, Lakshmi, that you have some insights into this. From what I understand, it's a potential area of research for
Yeah,
someone
yeah.
interested in.
We are also in the same boat. We are doing a lot of R&D to speed up the things, but we are not getting the clue before computation how we'll come to know how much time it will take or how much speed we need to do the processing. But yes, this is completely research area. Thank
So
you very much, Professor.
maybe I can just add, traditionally speed limits have been applied to extremely simple systems. So much of, since the conception in 1945 to, I guess around 2010, all the research was either at an abstract level or, single particle systems or a qubit or, there's some very simple systems. And there's much less research being done in complex many particle systems. One of the reasons why is because, people in particular coming from a condensed matter background know that there is something called Anderson catastrophe, from the point of view that you take a many-body system, you perturb it a bit, and it becomes already orthogonal to the so the notion of distinguishability is very abrupt. Yeah, it's very hard to quantify the in many-body systems. A tiny perturbation gives rise to a very different state. That seems to preclude the existence of speed limits, because essentially will mean that there is no good metric. This is not true. When you look at a many-body system and you do calculations exactly, and so that have been involved in part of these works, you do speed limits for many particle systems. Okay, you can see, what's the scaling of the speed of evolution, or what's the scaling in this distance between many-body quantum states. But overall, there's much less understanding. And even the works for quantum batteries, they are still using very simple systems, like some very well-structured spin chain, or even ensembles of non-interacting two-level systems. So, when there's much less done for spin glasses, for disorder systems, for the kind of effective description of neural networks. So I think that this is still, the research should move into this direction. I mean, we have a bit of work on the context of quantum phase transitions, which also has found applications, in particular in quantum metrology, the so-called quantum critical metrology, which is being investigated very much. But there you want to have also a very clean system, very regular, with a well-defined quantum critical point. So you understand how the criticality helps you to improve parameter estimation. Again, much less has been done, as far as I know, in the context of disorder glassy spin systems.
There is also a question from Nivetha Siva. Good afternoon, Adolfo. Is there any possibility to transfer power wirelessly in using quantum? I guess this is a generic question. Yeah. Is anybody want to answer this?
Transfer power?
It's not related to speed limits, I guess. It's just a question saying that is it possible to transfer power wirelessly for quantum batteries? I guess this is what it must mean. Nivetha, can you validate that that's your question? Is your question with respect to quantum batteries? Nivetha, you can unmute yourself. Transfer electricity using quantum. What does that mean?
Yeah, so this reminds me of, this is a brilliant new professor at the University of Massachusetts, Boston, Kazuki Ikeda, who has introduced these protocols for quantum energy teleportation. So maybe this is the closest I know, how to try to transfer energy. And of course, I guess my answer will always be positive. For any physical process with a state space, I'm going to be able to establish a speed limit. So I don't recall the details of the algorithm itself. I think it has already been implemented in experiments. And as a physical process, there will be a quantum speed limit that governs it, that constrains the efficiency, the speed. But I don't think this has yet been considered.
I'd like to add, like one Professor Adelfo mentioned one way to charge. There is just some works, and I think I have seen our archive how good they are. They like you require some mediator. So it's like if you can consider light as mediator, So there are some proposals you can charge the battery, remotely, but how they are feasible in the real life, that I don't know. One has to test. But I think the much bigger, way, like the Professor Delport is like just using this quantum energy teleportation.
All right. Any other questions? So, I'm going to use the remaining time to just ask one final question from all the panelists. Uh, One is, if you want to have say anything else that was not said about this topic, please take 2 minutes to do that. And then, what would you think is a great area to talk about, which is includes research as well as industry context in quantum, that you would like to see on the Quantum Pulse session in the future? So one is, say, if there's anything else you want to tell us about quantum speed limits, please take 2 minutes to do that. Let's do that first. And then give us some ideas about what you think would be a good topic for the future.
So I have a kind of some topics that I like and I'm confused about them. Is so you always learn a lot by pushing the ideas until they break down. And in the fundamental to the notion of speed limits is the idea that there is some evolution, there's some equation of motion that that you can describe. But what if you don't have it? There's some this is related to the how do you determine the passage of time? Can you always ascertain that time is flowing? How does time flow? And this is a bit philosophical. It's also, you can try to formalize it. I was actually working on this problem thanks to the John Templeton Foundation. And when we say that there's an equation of motion and we can determine how we go from one state to another one, this presumes in some sense that you know how time is flowing, and that typically this means you have a clock. A clock has a handle that is telling you how much time is passing. Now there are some some ideas there in the foundations of quantum mechanics that if you don't have a clock, if you cannot determine the passage of time, then you can only ascertain the passage of time as long as you determine that something is changing. Or let me say it differently. What in the do you know whether time is flowing when there is no change in a system?
Mm-hmm.
Yeah. So this is it's a beautiful kind of philosophical aspect, and you can at some point when I was working in Boston, we even tried to connect with some neuroscientists to see whether even human perception of time passage could be formalized in some sense under speed limits. I think this is completely open, but it's just great. Yes. So you can observe these ideas of speed limits, and there's even in the foundations of quantum mechanics, there's something called event-enhanced quantum theory, where essentially it assumes this from the start. You cannot determine the passage of time if you don't detect any change.
Mm-hmm.
And there is where you have to be careful, because now you don't have this time continuous evolution that we are assuming in quantum speed limits. Another thing that is also related to quantum measurements, is the same but restated in a different form. How do I know that something has happened? I'm making a measurement on a system. But then typically our description of measurements is not time continuous. I mean, you can use continuous quantum measurements as a framework, but very often there are other ways of doing it where you break this time continuity, and then you can, in principle, have transitions which are faster. This brings us to other applications of speed limits, which are also related to the coherence times or transition times. There was lots of work on the context of tunneling, which just got the Nobel Prize this year, macroscopic tunneling. So it was also, what's the minimum time in which a particle can tunnel or can transition to a different state, so-called jump times of a quantum transition. So do they take time? So for many years, people thought that transitions are instantaneous. Then at least in some settings, we understand that this is not the case. So these are other nice applications of these ideas of speed limits.
Thank you. I think that's very interesting. It might also throw some light into the definition of time itself, right? I mean, in terms of how discrete can time be if there are
Right. I mean,
limits to
when
that?
you look at an equation of motion, like the Schrodinger equation, you have this kind of idealized time. Yes. Some call it Newtonian time or whatever you want. Some time that is flowing. You presume you have a perfect clock with infinite precision to which you have access at all times. And if your error is faulty, well, then there are already studies about what happens. This brings decoherence. But if you don't even have a clock, then it's even more interesting.
Right. Thank you. Professor Pati?
Yeah, once I was thinking what you just mentioned. So we talk about time flows and time changes, but is it really possible to define the speed limit for time itself? At what rate time changes? Do you think it makes sense?
So I think if you look at fundamental physics, how it is evolving, there are a lot of other theories. I'm not a researcher, but I read a lot. So there are other theories on whether, just like you can quantize space, can you quantize time, right?
Those things
And
are there, yeah.
yeah, so then if time can be quantized and there is a limit to, there's a Planck's threshold for not just for space, but also for time, then of course there would be a speed limit as well, isn't it?
Yeah. So what is your take on this? Does it make sense, this question? At what rate time changes?
You asking me?
No, I asking Adolfo now.
Yeah, okay.
I mean, I like these questions. I mean, it's a bit like reversing. Yeah, you can still try to embrace information geometry and say that if you believe that actually this is a bit of line of thought that goes. I think I have seen it in the work by Seth Lloyd, where you assume that at some elementary process, logical operations saturate the speed limit. He used Margulis Levitin bound to try to derive general relativity. So you can just if you assume that you are saturating, that you have physical elementary operations that saturate the speed limit, then and you adopt information geometry and you have some no notion of distinguishability, then there's you cannot determine the passage of time. You will say that time is not flowing. So this is I mean, I don't. I would say it's an interesting question. I don't want to provide a definite answer, but I see some aspects where there are some ways of you can try to quantize time this way. I mean, but just from. I mean, of course. You have to fix the rules of the game, yes, because you can apply also speed limits to discrete processes like Markov chains, where you have discrete updates in time. So there you are by redefining your time with a clock, and you are just saying I'm just counting time steps, and there's no issue with that. This is not what I'm talking about. I'm also not talking about the quantization of time, as I wrote a book on time in quantum mechanics, where we introduced time operators. This is a bit more theory-driven approach, which from the point of view of information geometry has been superseded. Yeah, so we typically think of time as a parameter you estimate. But there is still this dichotomy, between the parameter you estimating the flow of time, and the idealized time you have in your equations of motion. And the question is, whether this idealized time can be justified or not. We typically always assume it's there, but yeah. I think it's a nice question. It's related to whether time flows when you cannot tell that there is change. If nothing changes, in your universe is steady, perfectly steady. Of course, it's an idealization, yes. But if no one can detect any change anywhere, that's time flow. Yeah.
Right.
Which brings me, okay, this will be more technical, but this is a beautiful problem also in the context of the coherence theory and what is called quantum Darwinism, where the environment monitors your system of interest, and your environment is very spread out. And in the idea of quantum Darwinism is that there is a redundant encoding of information of your system in the environment. So at some point, by monitoring local parts of the environment, or the local part of the environment that really have lots of information about your system. So this may Speed limits could, of course, be used to determine the coherence timescales and to put timescales in quantum Darwinism. But the other way around, you can also think of trying to use all surrounding environment to justify arrows of time. This is the canonical approach in statistical physics, but doing it in a quantum way, it's also interesting.
Right, and I definitely feel that I'm reaching two conclusions based on this discussion. One is that there's a very different audience for this conversation, and it's very super interesting. So maybe we need to split our podcasts into two groups. One is industry focused, and the other is more deeper into research topics. And definitely, time could be an interesting topic in the future from all perspectives, right? In terms of theories of time and bringing in the quantum speed limits, as well as look at it from a quantum mechanics perspective overall, right? So that's what I'm gathering from what you're saying right now. And Bridge, you want to add something else in terms of a topic that you think we should cover?
Okay, so in this area that today discussion we have, or like you are asking in general?
For the kind of discussion we are having, is there any other research topic, need not be quantum speed limits, but anything else that you think is very interesting and happening and we should cover that?
Maybe one is like since like there are several companies designing this quantum computing platform, hardware platform, and this all the platform they have a different challenges. So if one can shed a light somehow like on those platforms like ion trap, superconducting circuit, and there are some optical setups, people will have the better idea, and then what are these platforms are kind of facing the challenges. And of course one can talk about the latest Nobel Prize.
With
And
quantum tunneling, yes, yes,
yes,
absolutely.
yes, that
So
will be
we did have one of the discussions in the past was around the computing platforms, but it was quite a while ago, and I think it's time to maybe a lot has changed since then. So maybe we can have that again. And so we have three interesting topics from this discussion, and with that we are coming really towards the end of the session. We have 5 minutes which we can give back to everyone unless somebody wants to ask a question or say something. Uh, so one last opportunity to speak, both to the participants and to the speakers. If not, we'll wrap it up. So Dr. Rohini
So
Srivatsa says, yeah, go ahead.
I can talk something. See, right now I'm seeing like a lot of effort or time we from the service industry is putting into quantum security,
Mm-hmm.
post quantum cryptography or quantum security. Can we? Is there any session uh, on this particular area that will be more
Yes, yes.
interesting?
So, Mr. Lakshmidhar, if you, we have a YouTube channel. QETCI has a YouTube channel, and the recordings from the past Quantum Pulse sessions are included there. There are at least two past sessions which were focused on quantum security.
Oh, okay.
Let
I'll
me,
go through that.
yeah,
Sure.
please go through that and drop me an email. It's an evolving topic, so I'm suspecting that in the future also we'll have some other topics like that.
Okay. Okay. Thank you. Thank you very
And
much.
Professor C.S. Unnikrishnan has mentioned that some aspects of physical time is discussed in my book Gravity's Time. Yes, I think I heard you speak about it. Did you give a lecture at TIFR Hyderabad, Professor Unnikrishnan?
Well, I have talked about it, but nobody typically listens.
No, I think I was attending that lecture. Happened to be
Okay,
visiting
okay.
TIFR, and I think
I
I
just
heard you
mentioned
talk.
since discussion came up, I'm not the quantum aspects, but what exactly is physical time as we understand it, and what can sort of change it. I mean, my basic thesis is it's all under gravity's control,
Right.
but
Sure.
this is not the occasion to
Yeah, we'll go
say
into
further.
depth maybe in a future session on this. Yeah. All right. This is very interesting. Thank you so much to Professor Pati, Professor Del Campo, and Mr. Brij Mohan for sharing your valuable insights and your experience. And thank you to the audience, very participative, a lot of questions. Overall, thank you. I really enjoyed the session myself. Being a moderator, that is usually a difficult task, but I think we should do more such sessions. And wish everyone a very good weekend. This is the end of the day, Friday, and a perfect way to end it, like Rohini Srivatsa has said. Bye bye, everyone.
Thank you so much.
Thank you.
Thank you, Rena. Thank you,
It's been
Adolfo.
fun.
Thank you, everyone.
Thanks, everyone.
Thank you all.
Yes.
And Professor Uni Krishnan. So thank you all. So. Yeah.